Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, today we are going to start a new series. Yes, it is MySQL. Welcome to MySQL Bootcamp series. Yes, it's your hands-on journey into the world of data, databases, and dynamic applications. Whether you are building a career in web development, data science, or software engineering, mastering database is non-negotiable. Dear friends, imagine a world where every product order, bank transaction, and hospital visit had to be recorded manually in separate file. Non-central structure, no real-time updates, and no recovery from mistakes. That was the reality before database system. Now imagine logging into your Amazon account, checking your cart, and instantly seeing your saved items. That's the power of modern database. Invisible yet indispensable. Let me just start with the introduction to database system. Yes, this is the starting point of our journey into the world of data management. A domain that's essential to almost every industry today. Whether it's your social media app or your bank or your university registration portal, all rely on a robust, reliable, and scalable database system. Dear friends, in this video, we will explore what database systems are, why they are necessary, and how they have evolved to solve complex problems. From ensuring data consistency to supporting concurrent users worldwide. We will look at the system's inner working, the structure of data, how users interact with it, and how modern application depends on it every second. Now let's define what a database system relay in. Dear friends, at the simplest level, it's a collection of interrelated data, organized, structured, and stored in such a way that it can be efficiently accessed and updated. But a database is not just a storage file. It's governed by a software layer called Database Management System. We just let it know as DBMS. Think of that DBMS as a brain of the database system. It interprets your requests, maintains integrity, manages security, and ensures that data is updated correctly, even if your system crashes in the middle of the transaction. So, when you book a ride, transfer money, or stream a movie, the DBMS ensures that the data you need is retrieved, validated, and stored without any glitches. So it acts as the middleman between the raw data and your application, making sure everything runs smoothly. In the business world, databases are mission critical. In sales, they store customer profiles, order histories, and product inventories. In accounting, they track invoices, payments, and financial audits. HR systems uses database to store employee records, payroll information, and tax compliance data. Dear friends, in manufacturing, databases manage supply chains, production, schedules, and quality checks. In banking and finances, database handles sensitive operations like customer identity, verification, real-time balance updates, and fraud detection. And towards university, yes, that depends on databases. It manages students' enrollment course offerings, class schedules, and gradings. Every large organization is powered by a robust database system under the hood. And dear friends, databases are not just for big business. They touch our everyday lives. When you book a flight, the airline database updates seats availability in real time. When you stream music, the app fetches song data from a massive cloud database. So here your telecom provider uses database to log calls, messages, and mobile data usage. So online retailer track your purchases and use recommendation engine driven by database to suggest what you might want next. And even GPS navigation apps store location data, route networks, and live traffic updates using specialized spatial database. Dear friends, in short, database are the silent partner behind every modern interaction. Before modern databases, business stored information in flat files that is unstructured and spread across multiple formats. This led the data redundancy, the same data being repeated in different files, and inconsistency, where different files said different things about the same data. Accessing data were cumbersome. Yeah, a new task required writing a new program from the scratch. Data was isolated, hard to integrate. Worse, integrity rules like salary must be positive were buried deep in code and were hard to maintain or enforce. And what about the result? Of course, fragile system, prone to errors and inefficiency. So enter the modern database system, a structured, centralized, consistent solution. Different traditional systems also lacked robust error recovery. So imagine transferring money from account A to B. If the system crashes half the way, you could lose money or create imbalance. Here databases solve this using atomicity. So ensuring either the entire operation completes or nothing happens at all. So they also enable concurrent access. Multiple users can access and update data simultaneously. So without corrupting it, for example, two people can withdraw from a shared account without affecting each other's transaction accuracy. And here dear friends, lastly, databases offer granular security. You can control who sees what. For instance, HR can view salary data while a project manager can't. And here the core strength of database system lies in their ability to present multiple views of the same data. Not everyone needs to see or interact with the data in the same way. Imagine a university database. A student sees their grades and course schedule. A professor sees class rosters and grading interfaces. An admin sees records for all students. All this built from the same data, but through different views tailored to the user. Under the hood, database achieves these through data abstraction, a method that hides unnecessary complexity. Users are not concerned with how the data is stored or how it's retrieved. They only see what they need. This makes the system cleaner, safer, and for more scalable. Dear friends, a data model defines how data is organized, related, and constrained. Think of it as a conceptual framework, like a blueprint of your database. So the most widely used is the relational model, where data is stored in tables. But there are others too. That is, the entity relationship model is greater for design. It maps real entities like student or course and their relationship. And here next comes the object-based model, which are used in complex applications where data has behavior and identity, such as the multimedia system. And of course, semi-structured models like XML or JSON, which are used in web service, where flexibility is essential. And dear friends, earlier those hierarchical and network models were used, which imposed rigid relationship. And modern system prefers flexible, expressive models for broader application. Dear friends, the relational model introduced by Code in 1970s, and that revolutionized data storage. It organized data and relationship. It organizes data into relations commonly known as tables. Each table consists of rows, which is also called as tuples, representing records, and of course the columns, okay, which are we just specify it as like attributes, and of course representing fields of data. For example, a table named, for an example, if we just say instructor may have columns like ID, name, department, and salary. So the beauty of this model is in the simplicity and power. You can use a mathematical foundation, that is relational algebra, to perform operations like selection, projection, and joins. These operations are very much intuitive and forms the basis of querying the SQL. Dear friends, let's visualize this with an example. Here's a table called an instructor. Okay, and here we just have ID, name, department, and salary. And kindly just observe, dear friends, when we just have a particular ID towards this, okay, and he just belong to history. And here, of course, each row is one instructor, each column stores the particular attribute. Now, what if we want to find all instructors that of physics department? And here a simple SQL query can retrieve that with ease. And dear friends, relational tables also support keys, unique identifiers like an instructor IDs, which help maintain data integrity and links related tables like instructor and department via foreign key. So this relational linking is what given databases their real power. One of the important concept in database design is the three-level abstraction. The physical level, of course, this is the lowest level describing how the data is stored. Disk formats, memory layouts, and indexing strategies. And here towards the logical level, of course, this level describes what data is stored and what relationship exists. For an example, an instructor has an ID, a name, and department as salary. And here the view level, of course, this is what the user sees. A finance manager might only see names and salaries, while a course scheduler might only see IDs and department. So this layered structure, of course, makes the system flexible and secure. Developers can change physical storage method without affecting how the user views the data. Of course, thanks to the concept of data independency. And difference to better understand databases, we need to distinguish between schemas and instance. And difference as schema defines the structure. It's like the database blueprint. For instance, defining that a table, a student has an ID field, a name and a major. And an instant is the actual data stored in the database at a given time. So like the specific record of a student enrolled this semester. This is similar to programming. A class defines the structure, that is the schema, while each object is an instant with actual values. Let me just differentiate between. So here, kindly just observe, logical schema describe tables and relationship. And here, physical schema describe how tables are stored on disk. And here together, these abstraction allows database to have or to be both high level and deeply optimized. Now let's talk about one of the most powerful feature of modern database, that is physical data independence. Difference, this means we can change the physical storage data or details like indexing, strategies or file organization or even the type of hardware without modifying the logical scheme and application programs. And why is this important? Yes, of course. Let's say your organization upgrades from hard disk drives to solid SSD storage for better speed. You can make this change internally without disturbing the application software or user experience. And given this separation of concern is what makes database scalable, maintainable, and future-proof. It allows developer to optimize performance while keeping the user interface and data structure stable. Let now shift the focus to one of the core component of SQL, the data definition language, DDL. Difference, DDL is all about structure. It used to define the schema, that is the framework or blueprint of your database. Using this DDL, you tell MySQL what table to create, what columns each table should have, and what type of data each column should store. For an example, let me just have a create table. And here, of course, I just specify an instructor. So here ID is character, name varchar 20, department varchar 20, and salary in numeric. And this creates a new table named instructor with these 4 fields as ID, a name, a department name, and salary. But DDL does more than just defining table. It also specifies integrity constraint, such as setting a column as a primary key, which ensure that each row has a unique identifier. And next it just goes with a foreign key, of course, which link tables together and enforce referential integrity. And authorization rules, such as defining who can view or modify a table. All this structural information is stored in the special system maintained space called the data dictionary, or we can just specify as like a system catalog. This acts like a metadata repository, storing definition, relationship, and constraints of all database objects. Dear friends, in short, DDL lays the foundation of your database. It's like setting up the rooms and rules in your digital house before you bring in the furniture. That is the actual data. And here, once the database, the structure is placed using DDL, we need a way to interact with the data inside it. So this is where data manipulation language, that is DML, comes into play. And here DML allows us to insert new data into tables or query existing data, update records, and delete data when it's no longer needed. For an example, let me just add a new instructor. So you might write, of course, insert into instructor. Okay, so insert into instructor, this is the exact table name, and of course we have to write values and here the exact data, and of course about that ID and the name and the department and salary. And here, dear friends, there are 2 types of DML, that is of course procedural DML and declarative DML. And here this procedural DML, this is more like writing a recipe. You have to specify what you want and how to get it. This approach offers greater control but require more work. And here going for declarative DML, this is what like SQL. So here you only describe what you want and let the database figure out how it get it. So this is simpler, more readable, and more common in modern system. Difference, think of it like this. Procedural DML is like telling a chef each steps to quick your meal, while declarative DML is like placing an order from a menu and the kitchen handles the execution. So this declarative nature makes DML in SQL not only powerful but also user friendly and high maintainability. Let's bring everything together with a simple yet powerful SQL example. Suppose you want to list the name of all instructor in particular department. Here it is a computer science. So in the query, of course, select name from instructor where department name is equal to computer science. So here what's happening? Select name. Of course, you tells the database, I only want the name field. And from instructor, of course, specifies the table where querying. And of course, where condition. So here the condition is department is equal to computer science. So filter the results to only those who department is computer science. So this is a classic example of declarative DML. You specify what you want and the database engine handles the how. So it optimizes the path, checks permission, and fetches the result efficiently. But remember, SQL is incredibly powerful for data manipulation. It is not a full-fledged programming language. It does not support loops, conditional logic, or user input in the same way as general purpose languages like Python or Java does. So that's why in real world application, SQL is often embedded inside other programming environment. For an example, a Python script might collect user input and then pass on an SQL query to the MySQL server to fetch or update the relevant data. So this combination SQL for data and Python or Java for logic and interaction creates dynamic responsive data-driven application. Difference, designing a database is not just about storing data. It's about organizing information in a way that supports efficient, accurate, and meaningful use. Database design happens in two stages. That is logical design. So this is where we decide what data to store, what are the entities, what are their attributes and relationship. For an example, in a university database, we decide to store student, course, instructors and enrollment. So these step answers what information do we need. And here physical design, this is where we make decision about storage, indexing, strategy of file structure and optimization technique to ensure fast access, scalability and reliability. Good database design requires both business insight, that is what to store, and technical foresight, that is how to store it efficiently. And difference that poor design can lead to performance bottlenecks, data anomalies and high maintenance cost. And at the heart of database management system lies its engine, a set of modular components that works together to manage data storage or retrieval and security. And here the major component here is of course the data manager. So it thinks of this is as a warehouse manager. It handles disk storage, memory buffers, indexing and file access. Next, query processor. So this component interprets SQL commands, check for the correctness and finds the most efficient way to execute queries. And the next, transaction manager. So responsible for ensuring data integrity in a multi-user environment. It handles atomicity, consistency, isolation and durability. Yes, what we just say as a property. Togetherness, these components turn user requests into optimized operation, ensuring data is retrieved quickly, updated safely and protected from crashes and conflicts. Difference, the storage manager is the bridge between high-level queries and low-level data storage. Its responsibilities includes, of course, managing disk, that is space and memory buffers, handling files, organization and indexing, and enforcing authorization, that is who can access what, and integrity constraints, that is rules like salary should be always greater than 0. And difference, it interacts directly with the operating system's file manager to store and retrieve records efficiently. So the store manager ensures that data operations are not only fast but also safe and consistent. And difference, to operate efficiently, the storage manager use key internal structures, that is data files, that is these hold the actual database records. And next, data dictionary, metadata repository, that is this is like the brain. It stores schema, constraints and definition, data about the data, and indices. So these are lookup tools, just like an index in a book. So helps you to find a topic faster. A database index helps locate records quickly. So for instance, if you're searching for a student by ID, the index can jump to the exact row without scanning the entire table. So these structures are essential for achieving fast, reliable performance and scale. And the next state is the query processor. This is the intelligence unit of database management. It handles DDL interpreter, that is converts schema definition into internal structure stored in the metadata. Next, a DML compiler that translates SQL query into execution plan. So it also optimizes queries, choosing the most efficient way to get the result. And next, a query evaluation engine. executes the low-level instruction generated by the compiler. For an example, a user might write as like select name from instructor where salary greater than 90,000. See, the query processor turns that request into series of optimized steps to retrieve only the needed rows using these indices or sorted files if available. And here, dear friends, query processing involves three important steps: parsing and translation. So the SQL query is checked for syntax and translated into an internal representation. Next, optimization. So multiple execution plans may be possible. So the optimizer picks the one with the lowest cost in terms of time and resources usage. And next, evaluation. So the final query plan is executed, data is fetched, filtered and returned to the user. For large datasets, smart query processing can make the difference between 3-second response and a 3 minutes wait. So let talk about a transaction. A transaction is a unit of work, a series of operations that should either happen completely or not at all. For an example, transferring money from account A to account B involves debiting on one account and crediting on to another. If something fails in the midway, the transaction must be rolled back to ensure consistency. And therefore, the transaction manager ensures that the database remains consistency. That is exact. Total balance does not change unexpectedly. And here, no transaction interference with another. That is isolation. And here, changes are durable even if the system crashes. That is durability. And the next, the concurrency control manager, of course, prevents conflicts when multiple users interact with the same data simultaneously. So a common scenario in modern as like multi-user system. And dear friends, the database can be set up in different architecture depending on the scale, performance, needs and network setup. And here centralized database, all data and computation occur on a single machine. Simple but not scalable. Client server, a central database server handles requests from multiple clients. This is the most common architecture. Next, parallel databases. User multiple processor with shared or separate memory to process data simultaneously, useful in data warehouse and analytics. And next, it is distributed data. That is spread across multiple geographical location. And here data is stored and processed closer to the users, improving performance and fault tolerance. And friends, each architecture has trade-offs in complexity, scalability and performance. And here a centralized shared memory system is the simplest type of parallel architecture. Here multiple processor access the same memory space. It works well for a small scale, high performance system. And here tasks that benefit from shared data like simultaneously or mini data analysis perform. However, it's not suitable for large distributed application. And as the number of processor grows, memory contention and communication overhead can become a major bottleneck. And dear friends, I just come on with database application, and which are often structured in layers to improve scalability, security and manageability. And here in a two-tier architecture, the client directly communicates with the database server. It's simple but tightly coupled, making it harder to scale up or update. So in three-tier tier architecture. That's an intermediate between the application server, between the client and the database. So the client sends the request to the application server where the process logic and communicates with the database. So this is the exact architecture used in most modern web and enterprises application. And three-tier system offers better load balancing, separation of concerns, and centralized control, essential for enterprise level systems. And yeah, that's wrap up of our introduction of our MySQL bootcamp. So you now have a strong understanding of what a database system is, why it matters, and how it serves as the foundation for everything from enterprise software to the applications we use every day. And dear friends, in the next session, you will learn how to install MySQL on your system and create your very first database from scratch. We will move from theory to practice, setting up the environment where all your future queries, tables, and applications will come to life. So stay tuned, and I will see you in the next video where we begin building our own database. Thank you, dear friends. Happy learning.